like to take a look with you at this problem from section 4.6, which is about linear approximations. Okay, now one thing to keep in mind when we talk about linear approximations, this concept is really something we've seen already since the very beginning of the course. Because linear approximations are really the same concept as tangent lines. Okay, so when it's asking us to find a linear approximation, it's asking us to find a particular tangent line. The terminology is different here, mainly because we're using it for a different purpose. So when we think of a linear approximation, what we're doing here is we're saying, what's the best line that we could replace the original function with so that it's a really good approximation near a particular point. And the point matters. The linear approximation would be different if we were looking at a different point on the graph. So in any linear approximation problem, you'll be given a function, you'll be given a point, and you're looking for the linear approximation for that function at that point. So I wrote out this formula for the linear approximation. Again, this is perfectly consistent with what we already have seen and discussed as the tangent line to f at that point. So keep that in mind. So just like we would if we were looking for the equation for a tangent line, we're going to look at evaluating the function at that point. That's our f of a. We want to find the derivative, in this case using the quotient rule, or you could use the chain rule if you prefer, and evaluate that derivative at a. That'll give us the slope of our line. So here's our linear approximation up here. L of x is equal to 1 minus x. Part B of this problem says use the linear approximation to estimate f of negative 0.1. So this is, again, going back to what I said about how we're using this line that we are calling the linear approximation, but we could call the tangent line. We're using it here to estimate a value. We're using it to estimate the evaluation of f at a point near a. So a is 0. We're approximating the value that f takes at negative 0.1. And we're plugging into L of x to do that. So what I wrote here is f of negative 0.1 is approximately L of negative 0.1, which is 1.1. Okay, now you might say, well, gee, why don't I just plug in negative 0.1 to f in the first place? And of course, we could certainly do that. The point of this is just to see that if, for whatever reason, if we want to use a line because it's a simpler type of function than the original, then what's the best line to do that? And how good does it approximate? And that gets at what part C says. Compute your percent error in your approximation, and they give us this formula. Okay, so we're going to use the exact value, what we would get if we plugged into f, but we're also going to use the approximation, what we found in part B. And this formula will tell us how far apart our approximation is from the exact. So the approximation was 1.1. The exact is 1 over 0.9 or 10/9 or 1.1 repeating. And the difference is 1%. So it's a 1% error. And what we would expect in general is that the further away we get from this point, the less useful this approximation is in order to, substitute for the original function. If we're very close to A, then the linear approximation is more useful. It's going to tend to have a smaller error. But because we're not talking about a line to begin with, a line is only a good substitution nearby the point. The further away we get, the more they're going to tend to deviate from each other. Okay, so that's the concept of linear approximation. I hope you found that example helpful. We'll see you in the next video.